everyone. My presentation is we're going to be predicting Marbled Murrelet through LiDAR. So before we get into that, a little bit about me. I'm Kane Finders, and currently I'm a student trainee at the Bonneville Power Administration in their Environmental Compliance Department. And I'm also currently pursuing a degree in geomatics at the Oregon Institute of Technology, and previously I've worked with Metro. So in this presentation, first we're going to go over what do we need to know, the prerequisite knowledge before getting into this, and then some previous attempts at predicting Marbled Murrelet and the plan for making our model, and then what data are we working with for executing the plan, the variables that we need to extrapolate, how we make the model, and then finally the results, how does it compare with other models, and our next steps. So first, what exactly is the Marbled Murrelet? First of all, it's categorized as an endangered species by the U.S. Fish and Wildlife Service and primarily lives off of the west coast in Washington and Oregon area. And it nests in forests and old growth forests on platform trees. Construction and other loud or disturbing activities can disturb the breeding of these birds or even harm them. And so this is where us as environmental compliance specialists come into play. We look at the proposed action and see what kind of disturbance that could have on different plants, species, or other environmental factors. And so some previous studies, there's one that comes out of OSU for modeling Marbled Murrelet habitat using LiDAR derived canopy data. This is the study that we are going to base our project off of here at BPA, and use it as our starting point. And there's another one that we will be comparing to, which is the Maxim model, which was developed by the United States Forest Service as part of their forest plan for predicting Marbled Murrelet. We currently use this model within our GIS system for seeing the probability of habitat. And before we get any further, this is a very early step in our pilot project of integrating LiDAR-based data into our NEPA workflow. And so what this means is that we have a workflow we go through, and right now this data isn't set to be used for predicting species. We're very early, but at one point we will get there, but it's just not right now. So first, let's look at what data we are working with. So this is the LiDAR point cloud for Blinn radio site in Washington. And right here is a helicopter flying over. This is the actual picture, and this is the data that the helicopter collected with our high-resolution LiDAR scanners that we use, which we fly over our facilities and transmission lines on a 2-year repeating basis. And so as we zoom into these trees, we can see actually how high resolution this data is. We can see the individual branches almost on those trees. And so first we imported this data into our GIS Pro, and this is where we're doing most of our modeling. And so this is from the OSU study led by Martin and Raphael, and these are the 6 variables they used to create the model. In this project, we'll be focusing on the first 4. So here is the percentage of all returns above mean capacity height. That's the first we'll look at, and then the 99th and 10th percentile of height distribution on first returns, and then the percentage of first returns above the modal height. And so I'll get into how I made all those models, but these are the 4 we will be focusing on. Oops. And these last 2 we haven't gotten to yet, but early stages will incorporate all these variables and even more later down the line. And so know about Fusion. This OSU study was originally done in Fusion. However, since our LAS files, which is the file that has our point cloud in it, is so large and such high resolution, the Fusion software crashed every time we imported it. But we are working on trying to get the Fusion software to work as trying to replicate what previous studies have done so we get a good starting off pace. But in turn of that, I recalculated the mathematics used on that Fusion, within Fusion, to create those metrics and variables that we're going off of. And then I did that in ArcGIS Pro, so get similar results. And so the first thing we have to do now that we have the LiDAR data in ArcGIS Pro is generate the canopy raster. So this is the canopy raster, and you notice that it's pretty high resolution. These are foot-by-foot cells everywhere, and so right here you can see the guy wires and the radio towers. We have the road over here, and most importantly, the tree canopy all on here. So to get the canopy raster, what I did is that I just used the model builder script and ran the math to get the DTM. And we also created 2 of them, one for the first returns and one with all returns, because some of the variables needed only based off the first and some on all. And so now that we get to creating the variable rasters, we used a variety of the available geoprocessing tools to calculate the variables in the project. I'm not going to go through every single step I did to make these, but I think the most important one that I used was the focal statistics, which is once we ran all the calculations, we downsampled into a 50-foot by 50-foot cell. This is still a small size compared to current models, such as the Maxent model, which is a 50-meter by 50-meter cell. So we're still getting a much finer resolution with a 50-foot by 50-foot cell, but in the future we can look at making that more high resolution. So this is the first variable we talked about, which is the percentage of returns above the mean canopy height. This is the 50-foot by 50-foot cells, so it's a lot more blurrier than the previous canopy raster. And then here's another of the all first returns above the modal height. So again, we see the road's black because that's 0, 0, and we just see it throughout the canopy height of different varying scores. And the 10th percentile on the first returns, you might be asking, why is there a lot of black, a lot of zeros within this? And that's because when you hit the ground, returns a 0 value. And since a lot of them may be hitting the ground, that's why we get a lot of those 0 returns. That creates the 10th percentile. And then 99th percentile is again going to be those higher canopy heights. See, these are blazing white because these are the very highest in that cell. And we also see a lot over here. And so now that we have those 4 variables out of the way, how do we create the actual model? As again, we created the focal statistics, so they're all at the same exact cell size of 50-foot by 50-foot. This is important to making the model to make sure that all the cells match up. And we multiplied each raster by their coefficient value set forth in the OSU paper that I talked about earlier. There'll be citations at the end with links to these presentations or the other research papers that you can take a look at. And so the formula was basically the first raster times that variable plus the second raster times that variable, and so on, until we get our final model. And so let's take a look at that final model. So here is the final model we created. Red is the highest probability for Marbled Murrelet, and green is the lowest. You'll see here is blazing red. Marbled Murrelet are not nesting on our radio towers. The reason they are red is because they match the statistics of what a Marbled Murrelet would want to nest in, but the model obviously doesn't know what a tree is versus a radio tower. But we do see something else, is that this green line, this is where the road is. So we're seeing that there's no probability for the nest on the road. But we are seeing in these hot spots, Marbled Murrelet would like to nest. And so let's compare it with the current Maxent model. So overlaid on top of this is the Maxent model. Again, I used the 50-meter by 50-meter cell size, and what I did is I translated that raster into points that we overlaid on the map and scaled them. So how does it compare? Well, we see right here, the colors are matching over here, which is good. And then we also see a lot of green here, green overlaying where the red radio towers are, which is to be expected. One thing to take in mind, though, is that this shouldn't match completely. And the reason is that both of these models are measuring very different things. And it's using, the Maxent model is using satellite imagery and land trender data, while ours is using LiDAR derived canopy data. So it makes sense that it doesn't match. But what I do see is that in the extremes is where we match. So the very red matches, and in the green, we do have matching there. So that gives me a pretty good hope that we are on the right track. And so how did this model hold up? Well, as I said, this isn't an apples to apples comparison with the current Maxent model we use. They measure different variables with different data sets, and this is why we didn't perform a regression between the 2 over phi and R-squared values, because it's not a fair match, and it wouldn't make sense the data we get out of that regression. So how then do we model the actual accuracy of these models? Well, that's when we go out into the field and perform a field verification. So you go out to Blinn radio station, Washington, and see in those high probability areas, is there actually marbled murrelet nesting there? And if there is, then we have a pretty good hope that our model is holding up pretty well and we can move on to our next steps. And so what is next? Well, first thing we do is make a model incorporating all of the variables. As we said, this was just the first 4 in that paper, but we incorporate 2 more in that paper and also much more. Say, what is the current road network looking at? What is the current and already there disturbances that may affect? How old are these trees? What is the growth in the forest? And what, say, logging activities taking place? Incorporating that all into the model will make it much more accurate and reliable to use. And then we also want to try getting that Fuchsia software package working. It's been what has been being used for these LiDAR analysis, and we want to see if we can get it to work to make sure that we're on the right track along with everyone else. And then again, as I said, field verify the model. And then also, if we want to use these in our NEPA analysis, we're going to be working with the U.S. Fish and Wildlife Service and other agencies to develop a programmatic that we can use to institute these into our workflow. Then also there's the potential to work with the Pacific Northwest National Laboratory to harness their AI and machine learning technology to potentially get our data more accurate, more reliable. But this is something way in the future, and also implementing our findings into the NEPA workflow. These are 6 steps we're going to take to make our model more accurate, more reliable, and use it within our workplace. However, these 6 steps will be taking place over years. This isn't something that tomorrow is going to be finished. This is something that is in very early stages of development, but I am excited to be on the track to getting to where we have more accurate, more reliable data to work with. And so for our bibliography, first this is the OSU, this is actually the MaxEnt model used by the U.S. Forest Service, and this is the OSU study done with the OSU study to get that done. Is there any questions? There's contact information there if you want to reach out. Go ahead.
The bird species, are they impacted by habitat fragmentation from roads?
Yeah, so basically when you go in to create a road, you're going to clear cut that road area. Yeah. And what that does is not just clear cutting it, but that noise also drives out the species from that area.
Okay.
And can disrupt breeding, and it can even kill some of the birds depending on what happens. So that's why we perform these NEPA analysis, is to make sure that the actions we're doing doesn't harm the wildlife, and if it does, what mitigation we can go into place to make sure we have the least amount of impact possible.
How is this data collected?
Yeah, so the LiDAR point cloud data, Bonneville Power Administration, we have helicopters that fly with LiDAR scanners, and they fly over our transmission lines and our facilities. They do that on a 2-year rolling basis, so we have pretty up-to-date LiDAR point cloud data, and it is classified by contractor as well.
Do you have any ideas of how you would quantify like noise pollution and how that would be like mixed in a model?
Yeah, so any idea of quantifying noise pollution? So if you wanted to quantify noise pollution into our model, what we could do is beforehand, or go doing a site visit and collecting that noise data potentially, and going back and seeing how and integrating that. And this is where something maybe like a partnership with PNNL or other science divisions of Department of Energy could come into play. Because then we could ask, they have much more tools and are much more on the research side of things, and they could potentially advise on how to move forward with quantifying that data and building it into our model.
Do you have any plans to potentially work with LiDAR data that isn't downsampled as much? Because I noticed that you downsampled to 50 feet by 50 feet.
Yeah, so the reason why we downsampled to 50 feet by 50 feet is the data was taking the mean of a certain size, so that before we would have to downsample. But in the future, I would like to where we are getting that same exact precision that we're getting with our LiDAR data point cloud and using that. I don't see any reason why not we shouldn't be looking towards that future, and that's something we'll definitely be looking forward to as we move forward with this pilot program.
So from my understanding, you guys are creating, you know, a GIS hypothesis of where the birds would be, and then you're gonna go and ground truth it. And I'm curious if you flip that around and you know, if you have a place where you know these birds will be, and then, you know, you take that model or create a model on top of that and compare it, would that potentially change your data at all?
Definitely. Yeah, so this study was based, or our project was based off of the study done by OSU, which already provided those variables of like what exactly these variables and what mathematics go into it. And so this could actually create a new mathematics behind which variables we go out and collect and build into a new model. And this could be, the point you bring up, could be very helpful in, say, different areas where we don't exactly know what Marbled Murrelet like. So I do think that is something we'll look forward going into, is going out into the site and collecting data on where Marbled Murrelet nest and see what that habitat looks like, and then providing that into a bigger model. So yeah.
This is the NEPA process, as I understand it, would require you to like look at impacts to many different listed species in your project area. Do you guys have similar projects in the works or programs to kind of do this exact same sort of analysis for some of those other species?
Yeah, so for other species, right now within our GIS system, we have the critical habitats, but in terms of habitat prediction, we only have, like, I believe it's the north spotted owl, Marbled Murrelet, and one other bird species. So this pilot program could open the doors to creating more models based off of a lot more endangered species, whether they be animals, plants, birds, or anything else. And so I don't see a reason why not this pilot program could lead the way to using LiDAR and other remote sensing data to create high quality models to advise our NEPA analysis process.
What are some ways that you can remove some of the false positives that that are created here by, say, like high elevation infrastructure?
Yeah, so one way to do that is removing those artifacts afterwards with our raster processing. For example, right here is the canopy, and we see these high elevation infrastructure that he's talking about. And however, underneath it, we see there's actually a little bit of canopy right here and here. So we would find a way to remove that, and also see that this is just bare ground. And so removing those false positives would be very important. So definitely something we'll want to look into, and I do think we can do that.
Were the OSU LiDAR data collected with a helicopter with similar parameters? Have you looked at the statistics of the structure of the plane pod that you collect versus standard plane-based LiDAR? Because given that you're looking at the statistics, you can imagine that the coefficients might be different for the same kind of metric.
Yeah. So the OSU study, it was also collected on a plane. It was collected on a Cessna. It's much older LiDAR data, and as we know, LiDAR technology has been rapidly evolving over the past few years. I believe that LiDAR data was collected early 2010s, so there's definitely some range of difference. And also one thing that I can point out is that that study was ran on a different part of the United States. That was ran off the coast of Oregon. This is up in Washington. And so there's definitely room to improve our coefficient in terms, you brought up the coefficient of those statistics, and maybe different statistics altogether of what we put into this model. That's a great point you bring up. And so hopefully part of this pilot project is collecting feedback like this, so we can go back to the table and say, well, what do we need to change? What else can we do in the future to make this model even better? And if that's it, thank you all for listening.